The sound arrives before the movement. It rolls across the eucalyptus woodland in a rising cascade, a chorus of cackles that echo through the trunks and spill into the open understory. To human ears, it resembles laughter, boisterous, almost theatrical. But within the ecosystem, it functions as something more practical. It marks territory, coordinates family groups, and announces ownership of a hunting range. The laugh often comes at dawn, when light is thin and reptiles are slow. And sometimes it comes after the strike. The laughing kookaburra sits motionless on a sun-bleached branch, its large head disproportionately heavy for its body, its bill thick and powerful. At first glance it can seem almost comical. Bright eye, chocolate and cream plumage, posture relaxed. Yet its proportions are not decorative. The bill is a weapon engineered for impact. Unlike the curved talons of raptors or the slicing beaks of falcons, the kookaburra's bill is built for grasping and bludgeoning. It belongs to the kingfisher family, a lineage more often associated with diving into water for fish, yet this species has adapted fully to terrestrial predation. In Australian woodlands and suburban fringes alike, it hunts lizards, snakes, insects, small mammals, and even other birds with deliberate precision. The woodland floor below the perch appears still, but it is threaded with movement. A skink edges from beneath leaf litter to warm itself on a patch of sunlit soil. Thermoregulation governs its day. As an ectotherm, its body temperature depends on external heat. Early morning sunlight is survival currency, allowing muscles to contract quickly enough to evade predators. Yet that same basking exposes the reptile to aerial surveillance. The skink pauses, head slightly elevated, assessing vibrations and shadow. For many small prey species, freezing is a default defense. Remaining motionless can defeat predators that rely on detecting movement. In dense environments, stillness can erase outline. But in open woodland where dappled light alternates with shade, freezing may simply clarify position. The kookaburra tilts its head, one eye fixed downward. Kingfishers possess exceptional depth perception, aided by binocular vision and rapid neural processing that converts visual cues into precise motor commands. Unlike hovering kestrels or soaring eagles, the kookaburra does not need altitude to plan its attack. It relies on proximity and angle. Perched above the ground, it measures distance in silence. The broad bill parts slightly as it shifts weight forward, body aligned with the target. The strike is abrupt. Wings open only enough to guide the drop, feet extend, and the bill closes around the skink's midsection. There is no prolonged chase. The element of surprise is central to success. Small reptiles are capable of explosive sprints once fully warmed, but in transitional thermal states they remain fractionally slower. That fraction is decisive. Within seconds, the kookaburra lifts back to its perch, prey clenched firmly. What follows reveals the species' defining behavior. The skink writhes, muscles firing in reflexive escape patterns. The kookaburra responds by striking it repeatedly against the branch, a motion known as drop and smash or impact killing. Each downward swing accelerates the prey's body against a hard surface, causing concussive trauma that quickly incapacitates. This method is not gratuitous. It is biomechanical necessity. Small reptiles and snakes possess flexible spines and defensive bites. Subduing them without injury requires force concentrated through controlled impacts. The kookaburra's neck muscles and skull are adapted to absorb recoil, distributing shock in ways that protect the bird's own anatomy. Impact killing is common among kingfishers, Yet, in terrestrial species like the kookaburra, it has evolved into a highly refined technique. The bird times its blows rhythmically, adjusting grip to prevent escape, while ensuring the head or spine of the prey absorbs maximum force. After several strikes, the skink falls limp. The kookaburra repositions it head first in the bill before swallowing, minimizing resistance from limbs or scales. The entire sequence, from detection to ingestion, may last less than a minute. The woodland seems unchanged. Cicadas resume their droning. Leaves rustle under faint wind. But the predator has removed a node from the food web. Reptiles such as skinks regulate insect populations. In turn, they are regulated by birds like the kookaburra. This layered predation stabilizes ecosystems, preventing any single species from dominating. In suburban environments, where human structures fragment habitat, kookaburras often exploit gardens and parklands as hunting grounds, adapting seamlessly to modified landscapes. Their tolerance for proximity to people has reinforced the misconception that they are merely ornamental wildlife. Yet beneath that familiarity lies a consistent predatory role. The laughter that follows may be territorial reinforcement or social cohesion rather than celebration, yet the timing creates narrative. Family groups, often composed of a breeding pair and offspring from previous seasons, share territories and assist in raising young. Cooperative breeding enhances chick survival, particularly in years when prey abundance fluctuates with rainfall. Nesting occurs in tree hollows or even termite mounds, linking the bird's life cycle to the presence of mature trees and invertebrate architecture. In this way, the kookaburra becomes part of a web of symbiotic dependencies. Termites construct mounds that provide nesting cavities. Eucalyptus trees supply perches and hollows. Reptiles and insects offer sustenance. Remove one element and the balance shifts. Thermoregulation shapes daily rhythms here as well. During the heat of midday, kookaburras may reduce activity, conserving energy and avoiding overheating. Panting and gular fluttering assist in dissipating heat. Early mornings and late afternoons, when reptiles transition between thermal states, are prime hunting windows. The bird's success is therefore linked not only to prey behavior, but to solar cycles and microclimate variation across the woodland floor. Freezing, as a defensive tactic, evolved under specific ecological pressures. Many predators are visually oriented toward movement. Stillness disrupts detection algorithms. However, predators that rely on vantage and patience invert this advantage. The kookaburra, perched and scanning, is not fooled by immobility when it has already marked position. A frozen lizard that hopes to blend into bark or soil may instead solidify its outline in the predator's focused gaze. The mistake lies not in the strategy itself, but in misjudging which predator is watching. Occasionally, the prey is more formidable, a small snake capable of biting. The same drop-and-smash technique applies, though with heightened caution. By repeatedly striking the snake against a branch, the kookaburra aims to incapacitate before the jaws can pivot into defensive strike. This behavior demonstrates how morphology and technique co-evolve. The heavy bill is both clamp and hammer, allowing a bird scarcely larger than a crow to subdue venomous reptiles with calculated force. The laughter rings out again, echoing across the canopy. It is easy to anthropomorphize the sound, to imagine humor in its cadence. Yet within the ecosystem, it signals occupancy and dominance. Other birds respond, adjusting their own spatial patterns to avoid conflict. The vocal display reinforces social bonds and deters intruders, reducing the need for physical confrontation. In the broader ecological context, the kookaburra's predation influences insect outbreaks and reptile distribution. By preying on small snakes, it indirectly affects rodent populations those snakes might otherwise regulate. Such cascading effects illustrate the complexity of trophic interactions in Australian woodlands. Each predator is a node in a dynamic network shaped by climate variability, fire regimes, and human land use. As light intensifies and temperatures rise, the woodland shifts into midday rhythm. The kookaburra remains perched, feathers slightly fluffed against the warming air, eyes scanning for the next movement. Beneath it, leaf litter conceals countless lives navigating risk through stillness and speed. Some will escape through timing, others will miscalculate. The bird does not rush. It waits for the freeze that becomes fatal. The laughter carries once more, reverberating through trunks and branches. It is not mockery. It is announcement, a reminder that in this landscape, survival depends on reading not only the ground, but the branch above it. Freezing can be camouflage, but when the predator has already fixed its gaze, stillness is simply the final pause before impact. Morning light spreads thinly across an Australian paddock, flattening the color of dry grass into pale gold and silver. The air is already warming, and with it comes movement. Crickets testing their legs, a field mouse weaving beneath seed heads, the faint tremor of life just below the surface. From a distance, the landscape appears empty. It is not empty. It is exposed. And exposure, in open country, is an invitation. A small falcon lifts into the frame, holding position against the breeze with a motion that looks almost mechanical. The Nankeen kestrel is slight compared to the heavy-bodied eagles that dominate the skyline, but its proportions are refined for a different kind of authority. Narrow wings beat rapidly, tail fanned and angled downward, body suspended in a fixed point in space, as if pinned to an invisible thread. This is hover hunting, a technique so precise that it reshapes how gravity and wind are used. Unlike larger raptors that rely primarily on soaring thermals, the kestrel converts headwinds into stability, facing directly into the breeze so that lift counters weight while wing beats provide minute corrections. The result is a living tripod in mid-air. The kestrel's body mass is low enough to allow prolonged hovering without exhausting its energy reserves, yet high enough to strike with force. Every feather participates in this equilibrium. Primary feathers flex independently to smooth turbulence. Tail feathers pivot to maintain orientation. Even the head remains astonishingly still, while the wings blur around it. That steadiness is not aesthetic. It is neurological discipline. The vestibular system in raptors integrates visual input with balance organs so that the image of the ground remains stable even as the body shifts. To hover successfully, the kestrel must lock its gaze onto minute disturbances, the flicker of a grass stem bending against the prevailing wind, the ripple of soil where a beetle tunnels upward, the faint shadow of a skink moving between clumps. Grassland from ground level offers the illusion of cover. From above, it becomes a translucent veil. The structure of open country favors site-based predators because vertical complexity is low. Trees and shrubs, when present, are scattered, and the density of foliage is rarely sufficient to obscure motion completely. Small mammals have evolved counter-strategies, cryptic coloration, erratic sprint patterns, burrows with multiple exits. But each adaptation carries trade-offs. A mouse that bolts across open ground exposes itself to any aerial hunter scanning from above. A mouse that freezes may avoid detection, but if the kestrel has already fixed its position, stillness becomes surrender. The kestrel does not dive impulsively. Hovering allows it to calibrate. Wind speed, prey movement, and distance are computed in fractions of a second. Raptors possess a second fovea in each eye, a region of high photoreceptor density that sharpens focus along the axis of attack. By tilting its head slightly, the kestrel aligns this fovea with the target, enhancing depth perception before committing to descent. When it does strike, the motion is economical. Wings fold partially, body angles downward, and gravity accelerates the drop. Unlike the dramatic stoops of larger falcons, the kestrel's descent is short and surgical, optimized for targets within a limited vertical range. The prey below, a house mouse grazing on fallen grain, has already miscalculated. Open paddocks near agricultural land provide abundant food, especially in seasons following harvest. Rodent populations can surge in response to resource pulses, creating what ecologists call eruptions. These booms are temporary, and predators track them closely. The kestrel's breeding cycles often align with prey abundance. Increased food availability translates directly into higher chick survival rates. Thus, the bird's presence over farmland is not incidental, but part of a dynamic relationship between climate, crop cycles, and rodent reproduction. As the kestrel descends, its talons extend. Though small, they are sharply curved and proportionally formidable. The grip strength required to immobilize a mouse or small lizard does not rely on sheer mass, but on precision placement. The strike targets the thoracic region or head, aiming to incapacitate instantly. Unlike scavengers, falcons must end movement quickly to prevent escape or injury. A successful strike is almost silent, a soft rustle of grass, a brief tremor, and then stillness. What distinguishes the Nankeen kestrel is not only its accuracy, but its adaptability. Across Australia, from arid interior plains to coastal farmland, it occupies a wide range of habitats. In hotter inland regions, thermoregulation shapes daily routines. Hovering under intense midday sun demands efficient heat dissipation. The kestrel pants subtly, increasing evaporative cooling through its respiratory system, while the pale underside of its plumage reflects some solar radiation. Early morning and late afternoon hunts are energetically favorable, yet the bird remains active when wind conditions support stable hovering. The relationship between wind and hunting success is so pronounced that kestrels often patrol road verges, where passing vehicles flush insects and create localized air currents. Insects form a significant portion of the kestrel's diet, particularly during warmer months. Large grasshoppers, beetles, and dragonflies are taken mid-air or plucked from vegetation. This dietary flexibility stabilizes ecosystems by regulating multiple prey populations simultaneously. When rodent numbers decline, insect predation compensates. When insect abundance spikes, kestrels respond accordingly. Such generalist behavior buffers the predator against environmental fluctuations and underscores its ecological importance in both natural grasslands and human-modified landscapes. There is an irony in its appearance. The Nankeen kestrel's soft rufous tones and delicate build can evoke a sense of harmlessness. Yet morphology belies function. The beak is sharply hooked, designed to sever spinal cords or tear flesh efficiently. The eyes, dark and unblinking during a hunt, reflect light with an intensity that reveals focus rather than gentleness. This juxtaposition between size and lethality illustrates a broader evolutionary principle. Predatory efficiency is not measured by bulk alone. In open ecosystems, agility and precision often outweigh brute force. Grassland itself becomes a trap because it magnifies error. Unlike forested environments where vertical escape routes exist and dense cover fragment sightlines, open paddocks offer few second chances. Once airborne predators establish dominance overhead, terrestrial animals must rely on burrows or rapid lateral movement to survive. However, lateral movement across uniform terrain creates predictable trajectories. The kestrel's hover reduces uncertainty. It waits for alignment, for the moment when prey crosses an exposed patch between tussocks. In that interval, the sky collapses into a point. Seasonal patterns further shape this dance. In years of drought, prey densities fall and kestrels may expand their territories or delay breeding. In wetter cycles, when vegetation flourishes and small mammals proliferate, nests in tree hollows or on cliff ledges fill with hungry chicks, demanding constant delivery of protein-rich prey. Both parents share hunting duties, and their efficiency in the air directly translates into the next generation's survival. Migration within Australia is subtle rather than continental. Many populations are resident, shifting locally in response to rainfall gradients and resource availability rather than undertaking long-distance journeys. The kestrel's presence also influences the behavior of other predators. Larger raptors may displace it from prime perches, while corvids sometimes mob it to protect nesting territories. Yet the kestrel's agility allows it to evade harassment with tight aerial maneuvers. Its relatively small size grants maneuverability advantages in cluttered airspace near fences, trees, and farm structures. As the morning advances, thermals strengthen and wind patterns shift. The kestrel transitions from hover to perch, settling briefly on a fence post. From there, it surveys the field again, recalibrating. The grass continues to sway, insects resume their stridulations, and rodents cautiously re-emerge. The ecosystem resets moment by moment, but the aerial knife remains poised. In this landscape, the misconception of weakness is itself a vulnerability. Small does not mean inconsequential. Delicate does not mean benign. The Nankeen kestrel demonstrates how evolution refines predation into a discipline of timing and balance. It is not spectacle that defines its success, but repetition: hover, assess, descend, reset. Each movement is a measured correction against wind and gravity. Each strike an equation solved with minimal error. The grassland appears calm again, yet calmness here is conditional. Above it, suspended in the invisible scaffolding of moving air, a small falcon rewrites the boundaries of safety. What looks like open space is in fact a stage, and every misjudged dash across its surface can be ended by a predator scarcely larger than a pigeon, but engineered by millions of years to function as a flying blade. The desert does not forgive hesitation, and along its fractured margins, where spinifex grass thins into bare red earth and sandstone ridges split the horizon, something moves with deliberate authority. At first it appears as a distortion in heat shimmer, a pattern sliding between rock shadows. Then the form resolves into muscle and scale, the perentie, Australia's largest monitor lizard, stretching nearly 2.5 meters from blunt snout to tapering tail. In a landscape that often feels empty, it commands space without noise. The perentie is not built like the reptiles that hide beneath bark or bask timidly at the edge of scrub. Its limbs are long and columned, shoulders rolling beneath thick, pebbled skin patterned in ochre and charcoal bands that break its outline against stone. The head is broad, eyes forward-facing enough to grant precise depth perception, and the jawline carries a tension that hints at mechanical force rather than fragility. It is easy to underestimate a lizard in open terrain. That mistake is common. It is also costly. Morning sun strikes the rock faces first, warming their surfaces long before the sandy flats. Thermoregulation dictates the perentia's opening move each day. As an ectotherm, it cannot generate sustained internal heat the way mammals can, but its physiology is far from passive. By orienting its body to maximize surface exposure, pressing its belly against warmed stone, and adjusting posture to regulate convective cooling, it raises core temperature efficiently. Warmer muscles contract faster. Warmer nerves transmit signals with greater speed. In the desert, the difference between 20 degrees Celsius and 30 can determine whether a sprint succeeds or fails. As the sun climbs, the perentia leaves the rock shelf and begins to patrol the interface between open ground and broken cover. Edges matter here. Ecologists refer to these transition zones as ecotones, areas where two habitat types meet and biological interactions intensify. Prey animals favor such edges because they provide both foraging opportunity and nearby refuge. A small kangaroo rat feeds in the open but dashes toward rock crevices at the first sign of danger. A ground-nesting bird selects scrub near stone outcrops to reduce exposure. The perentia understands this geometry not abstractly, but through evolutionary tuning. It dominates the very seams where risk accumulates. Its movement is not sluggish. Contrary to the stereotype of reptiles as slow, the perentia is capable of explosive acceleration. Powerful hind limbs extend in long strides, tail counterbalancing the torso as it surges forward in bursts that can exceed 40 kilometers per hour over short distances. This is not sustained marathon speed, yet it is enough to close the gap between perception and contact. The animal's aerobic capacity is unusually high for a reptile. Monitors possess a cardiovascular system more efficient than that of many other lizards, with a partially divided heart that improves oxygen separation. This anatomical advantage supports both speed bursts and extended activity in heat that would immobilize less adapted species. A rustle along the base of a shrub interrupts the stillness. A small euro, a type of wallaroo, has ventured closer to the rocks than it should. Juveniles are especially vulnerable during dispersal when inexperience collides with terrain complexity. The perentia pauses, tongue flicking in rapid succession. This is not idle habit. The forked tongue gathers airborne chemical particles and delivers them to the Jacobson's organ in the roof of the mouth, allowing the lizard to construct a scent map of recent movement. Chemical trails linger even when visual cues vanish. The desert writes its stories in molecules. The euro senses something and bolts toward the nearest rocky crevice. It believes distance is safety. What it underestimates is persistence. The perentie lunges, claws digging into sand, body undulating with coordinated force. The sprint is brief but decisive. When the lizard reaches the base of the rocks, it does not retreat. Instead, it climbs. Climbing is central to the perentia's dominance of terrain edges. Its claws hook into cracks, limbs pushing with surprising agility up vertical faces. The tail, muscular and heavy, acts as both stabilizer and lever. In rocky landscapes where prey assumes elevation equals refuge, the perentia transforms verticality into opportunity. It wedges its head into fissures, probing with tongue and snout, widening space with sheer force. Smaller reptiles, birds' eggs, even mammals that believed themselves secure in crevices become accessible. The bite, when it comes, is not merely crushing, but tearing. Monitor lizards possess recurved, serrated teeth designed to grip and slice rather than puncture cleanly. Combined with strong neck muscles, the bite delivers lacerations that can incapacitate prey quickly. There is ongoing scientific discussion regarding the presence of venom in some monitor species. While not as potent as that of certain snakes, secretions from mandibular glands may exacerbate blood loss and shock. Whether through mechanical trauma or biochemical contribution, the result is the same. Prey that misjudges the lizard's intent loses control of the encounter. The Euro escapes this time, vanishing deeper into rock. The perentie does not pursue recklessly into inaccessible cavities. It recalibrates, moving along the ridgeline, scanning for alternative targets. Endurance distinguishes it from ambush predators that rely on singular opportunities. The lizard can cover significant ground across the course of a day, weaving between outcrops, traversing sandy plains, investigating burrows. Its metabolic strategy balances energy expenditure with ambient temperature, reducing activity during peak heat to avoid overheating while remaining active longer than many other reptiles. Along a different stretch of terrain, a feral rabbit emerges from shade to graze. Introduced species have altered Australian ecosystems profoundly, and predators such as the perentie have adapted to exploit these newcomers. The rabbit freezes when it notices movement, banking on camouflage. But freezing near a terrain edge can be fatal. The perentie's binocular focus narrows. A second sprint launches across open ground. This time, the distance is short. Claws strike, jaws clamp, and the tearing bite ends resistance in seconds. Dust settles. The lizard adjusts its grip and begins to consume. Consumption is methodical. Flesh is torn in strips, swallowed with minimal chewing. The perentie's digestive system can process large meals infrequently, allowing it to endure periods of scarcity. In the arid interior, where rainfall patterns are erratic, such physiological resilience is essential. Food pulses may be separated by weeks of limited opportunity. Fat reserves accumulate along the tail and abdomen, serving as energy banks during lean times. Dominance here is not solely about predation. The perentie also intimidates competitors. Smaller goannas yield territory when confronted, and even wedge-tailed eagles may approach cautiously around a large adult. When threatened, the perentie can rear on hind legs, mouth agape, tail lashing with force, capable of deterring potential attackers. The display is not theatrical but functional, expanding apparent size and signaling readiness to defend. In ecosystems where encounters are frequent but energy costly, intimidation can prevent unnecessary injury. The misconception that a lizard will not chase often stems from observing smaller, more sedentary species. The perentie defies that assumption. It tracks scent trails across hundreds of meters, pursues prey with stamina, and returns repeatedly to productive zones. Its dominance of rocky cover extends beyond immediate kills. It shapes the behavior of species that share its range. Small mammals adjust burrow placement, reptiles choose basking sites carefully, and ground-nesting birds must weigh the proximity of stone against the risk of discovery. As afternoon light angles low, shadows stretch across the ridge. The perentie climbs once more to a high vantage point, body aligned with residual warmth radiating from rock. It rests, but the rest is conditional, head raised, tongue tasting the cooling air. In this environment, survival is a negotiation between heat, hunger, and terrain. The lizard's power lies not only in muscle, but in endurance, the ability to patrol edges repeatedly until opportunity aligns with readiness. From a distance, the desert may appear barren, but along its margins, life compresses into narrow bands of interaction. The perentie embodies that compression, turning terrain edges into arenas of advantage. It wins not because it is the largest creature present, but because it integrates speed, stamina, and tearing force with an intimate understanding of where prey will hesitate. Thinking a lizard will not chase ignores the evolutionary calculus etched into its limbs and jaws. Along the rocks and red earth of Australia's interior, that miscalculation is corrected swiftly and without spectacle. Night settles differently in Tasmania than on the mainland. The air cools quickly, sliding down from alpine ridges into damp eucalyptus forest and across button grass plains. Mist gathers in low pockets, and the last warmth stored in stones dissipates into the dark. Daytime hunters have withdrawn. The sky predators are silhouettes returning to roost, and the diurnal reptiles that ruled the sunlit hours are tucked into crevices and hollow logs. Yet the ecosystem does not rest. It shifts. A shape moves along the forest edge, low and compact, shoulders rolling beneath coarse black fur marked with a pale crescent across the chest. The Tasmanian devil is not large by global standards of carnivores, rarely exceeding a small dog in size, but mass is not the measure of its influence. Its head appears oversized, jaws disproportionately broad, and its gait carries a determined, almost mechanical directness. It is not the architect of the hunt in the way an eagle calculates from altitude or a dingo pressures from angles. It is the finisher, drawn not by spectacle, but by opportunity. The forest floor carries stories in scent. Blood from a wallaby injured hours earlier has seeped into leaf litter. A carcass lies somewhere beyond the tree line, partly concealed by bracken. The devil lowers its head, nostrils flaring. Its olfactory system is acute, capable of detecting carrion from significant distances, particularly in the still air of night, when scent trails remain undisturbed by thermal currents. Sound accompanies scent, a faint rustle of movement, perhaps the final struggles of an animal weakened by injury, echoes faintly through the undergrowth. Unlike cursorial predators that rely on endurance chases, the Tasmanian devil thrives on weakness. Injury and illness are signals that ripple through the ecosystem, and the devil responds to them with precision. It does not need to bring down the strong in open pursuit. It waits for the moment when something slips, missteps on wet rock, falls prey to infection, or survives an attack only to limp into shadow. In that moment, nature's accounting changes. The devil reaches the carcass first. It is a Bennett's wallaby, likely struck by a vehicle along a nearby rural road and dragged into cover by gravity or scavenging birds. The body is intact but lifeless. Here, the devil's specialization becomes apparent. Its bite force, relative to body size, ranks among the strongest of any mammal. The skull is reinforced, the sagittal crest pronounced, anchoring powerful jaw muscles capable of exerting crushing pressure. Teeth are thick and robust, designed not merely to shear flesh, but to crack bone. Bone crush commitment is not hyperbole. The devil consumes carcasses almost entirely, muscle, skin, organs, and skeletal elements alike. This efficiency is ecologically significant. In environments where nutrient cycles must be rapid to sustain plant growth, removing carcasses quickly prevents the proliferation of pathogens and recycles calcium and phosphorus back into soil systems. Devils perform a sanitation service that shapes disease dynamics and nutrient flow across Tasmanian landscapes. The first bite lands with audible force, ribs splintering under compression. The devil braces with forelimbs, shaking its head to tear through connective tissue. There is no delicacy. This is not a predator seeking to preserve hide or harvest selectively. It commits fully, consuming what others leave behind. Even fur and small bones are swallowed, later fragmented further, in a highly acidic stomach environment capable of dissolving dense tissue. Other devils approach, drawn by scent and sound. Vocalizations escalate into guttural growls and piercing screams that have contributed to the species' reputation. These sounds are less about aggression than negotiation. Devils rarely form structured packs, but they tolerate temporary aggregations around abundant food. Hierarchies emerge fluidly, determined by size, persistence, and willingness to engage in displays of dominance. Posturing, open-mouthed snarls, and lunges often prevent escalations to serious injury. Energy conservation remains paramount. The mistake theme unfolds subtly here. A wallaby that survived an initial trauma may attempt to hide, but its compromised mobility leaves it vulnerable to nocturnal scavengers that interpret weakness as invitation. Devils can and do hunt small prey, birds, reptiles, and young mammals, but they are most effective when finishing what others begin or when capitalizing on environmental accidents. Their opportunism is a refined adaptation to an island ecosystem where resource pulses can be unpredictable. Tasmania's climate shapes this strategy. Cooler temperatures compared to mainland Australia influence thermoregulation and activity patterns. Devils are primarily nocturnal, partly to avoid daytime heat and competition, partly to exploit reduced visibility that benefits a scent-oriented carnivore. During daylight, they rest in dens, hollow logs, burrows, or dense vegetation, emerging at dusk to patrol territories that may span several square kilometers. Their movement is steady rather than explosive, conserving energy while scanning for olfactory cues. A surprising layer of complexity lies in their social biology. Tasmanian devils are marsupials, and their reproductive strategy reflects this lineage. Females give birth to litters of tiny, underdeveloped young that must compete for access to the limited number of teats within the pouch. Only those that secure attachment survive the early weeks. This intense competition at birth mirrors the adult world's contest over carcasses, an echo of selection pressures that favor resilience from the first moments of life. In recent decades, devils have faced a profound evolutionary challenge in the form of devil facial tumor disease, DFTD, a transmissible cancer spread through biting during social interactions. The disease has decimated populations in parts of Tasmania, altering social structure and reducing lifespan. Yet, even here, natural selection operates. Evidence suggests some devils are developing genetic resistance or tolerance, demonstrating how, even in crisis, evolutionary processes continue to refine survival strategies. As the feeding continues, the carcass diminishes rapidly. Bones crack and disappear. Within hours, little remains beyond scattered fragments and darkened soil. In the absence of devils, such carcasses might persist longer, attracting feral predators or fostering microbial blooms. By removing the resource swiftly, devils limit opportunities for invasive species and stabilize ecological balance. Their brutality is functional, not gratuitous. A sudden rustle draws attention. A second wallaby, perhaps drawn by curiosity or misjudgment, edges closer than prudence allows. It limps slightly, old injury, not yet fatal. The devils pause, heads lifting in unison. Sound and scent confirm vulnerability. There is no elaborate pursuit. The weakened animal attempts to flee, but its compromised stride betrays it. One devil lunges, jaws locking onto hindquarters. The struggle is brief and chaotic, and within minutes, movement ceases. This is not a clean kill in the cinematic sense. There is no dramatic stoop from the sky, no calculated chase across open plain. It is a convergence of weakness and presence. Nature does not require elegance to function. It requires opportunity. As dawn approaches, the devils retreat to cover, bellies distended, fur smeared with evidence of the night's labor. The forest floor appears undisturbed to a casual glance. Mist rises again, and diurnal life resumes cautiously. The sanitation has been completed, nutrients redistributed, vulnerability exploited. In Tasmania's ecosystems, the Tasmanian devil embodies a critical truth. Survival is not only about strength or speed, but about what happens after something goes wrong. Injury, misstep, illness. These are openings in the fabric of resilience. The devil listens for them in rustle and breath, smells them in the damp air, and arrives with bone-crushing resolve. Nature does not need perfection to maintain its cycles. It only needs a single lapse, a moment of imbalance, and the finisher will follow. The northern Australian savanna wakes beneath a pale, expanding sky. Eucalyptus trunks rise like pillars from a carpet of dry grass and leaf litter, their bark peeling in long curls that collect at the base in copper-toned drifts. Termite mounds punctuate the flatness, and thin ribbons of shade stretch eastward as the sun lifts. In this mosaic of woodland and open ground, stillness is rarely empty. It is negotiation. Pressed against the bark of a paperbark tree, a frilled lizard waits. Its body is flattened vertically, limbs splayed slightly outward to increase surface contact with the trunk. In repose, it resembles an extension of the tree itself, mottled brown and grey scales breaking up its outline against fissured bark. The long tail trails downward, tapering like a root. For most of its life, this lizard survives by invisibility rather than spectacle. The frill, its most iconic feature, is folded neatly against the neck, barely visible, a pleated collar of skin supported by elongated cartilaginous rods attached to the hyoid apparatus beneath the throat. Thermoregulation governs its morning. As an ectotherm, the frilled lizard depends on external heat to elevate its body temperature to the range required for optimal muscle function. It begins the day oriented toward the sun, absorbing radiant energy through the darker scales of its back. Blood flow adjusts subtly to shuttle warmth inward, raising core temperature and accelerating metabolic processes. Only when muscles respond with speed and coordination does the lizard descend to forage. Its diet is primarily insectivorous: ants, beetles, termites, and occasionally small vertebrates. Insect abundance fluctuates with rainfall, and the savanna's wet-dry cycle shapes the lizard's annual rhythm. During the wet season, when vegetation thickens and insect populations surge, The frilled lizard is more active and more visible. During the dry season, it conserves energy, often remaining high in trees where airflow reduces heat load and predators are easier to spot. Vertical space becomes refuge. Movement below disrupts the balance. A predator enters the periphery, a dingo weaving through grass, nose low, eyes scanning. The frilled lizard detects vibration first, then scent carried on shifting air currents. Its body tightens against bark. Freezing is the first strategy, and in many encounters, it suffices. Cryptic coloration evolved precisely for this moment, disrupting the predator's search image and blending the lizard into textured background. But sometimes camouflage fails. The dingo lifts its head and focuses. It does not flinch. The transformation is instantaneous. The frilled lizard drops from the trunk to the ground, pivots to face the threat, and the frill erupts outward in a dramatic arc. The hyoid bones swing forward, extending the pleated membrane into a broad disc nearly twice the width of the head. The mouth opens wide, revealing a bright yellow or pink interior that contrasts sharply with the muted environment. The lizard rises partially onto hind legs, body elevated, tail counterbalancing. It hisses and lunges forward a fraction. This is intimidation, not armor. The frill contains no bone strong enough to deflect a bite, no spines tipped with venom. It is skin and cartilage, vascularized and responsive, designed to amplify perceived size and project threat. Evolution shapes such displays through selective pressure exerted by predator psychology. If enough predators hesitate in the presence of sudden expansion and color contrast, individuals with more pronounced frills survive to reproduce. Over generations, exaggeration becomes advantage. In many cases, the display succeeds. Birds of prey may abort a stoop when confronted with an unexpected, rapidly expanding form. Mammalian predators sometimes pause, reassessing risk. That pause is currency. It buys seconds, and seconds in predator-prey interactions are decisive. The frill also serves in intraspecific communication, particularly among males during territorial disputes or courtship. A larger, more vivid display can signal fitness, deterring rivals without physical combat. Sexual selection likely reinforced the frill's prominence, intertwining survival advantage with reproductive signaling. Thus, the structure embodies multiple evolutionary narratives layered into one membrane of skin. Yet, bluff depends on audience. The dingo does not retreat. It has encountered such displays before, learned that expansion does not equal harm. The lizard's strategy must shift. It pivots and runs. The sprint is startling. The frilled lizard rises fully onto hind legs, forelimbs tucked close to the body, and charges across the savanna floor in bipedal motion. This upright run, iconic in wildlife imagery, reduces friction and allows longer stride length, powered by strong hind limb musculature. The tail extends rigidly behind as counterweight, stabilizing rapid changes in direction. Speed is not sustained over long distances, but it is sufficient to reach the nearest tree trunk. Claws bite into bark, and the lizard ascends vertically with practiced urgency. Trees are not simply perches, they are escape corridors. The vertical plane offers angles inaccessible to many terrestrial predators. Once above a certain height, the lizard circles to the opposite side of the trunk, using the tree as a physical barrier. Here, the frill folds again, display abandoned in favor of concealment. The dingo, unable or unwilling to climb, moves on. The bluff bought time. The sprint completed the escape. This interplay between display and flight illustrates a broader principle in evolutionary biology. Defensive traits are rarely absolute. They function within specific ecological contexts and against particular predators. A frill effective against visually oriented birds may be less persuasive to a mammal relying on scent and experience. Selection does not produce universal solutions, it refines probabilities. The frill's vascular network also hints at additional roles. When extended, increased blood flow can assist in heat exchange, dissipating excess warmth through the expanded surface area. While primarily a display organ, it may contribute secondarily to thermoregulation in high temperatures. Multifunctionality is common in evolution. Structures that serve more than one purpose are often retained and elaborated. Predators that do not flinch force reality to intrude upon bluff. In such cases, the lizard's reliance shifts entirely to locomotion and habitat complexity. If caught on open ground too far from vertical refuge, the frill becomes irrelevant. A perentie or raptor may not hesitate long enough for escape. Here lies the tension between intimidation and vulnerability. The frill projects dominance, but the body beneath remains delicate. Juvenile frilled lizards experience especially high predation rates. Many displays are tested against adversaries that quickly learn to ignore them. Natural selection, therefore, balances exaggeration with energy cost. Growing and maintaining a large frill requires resources. If the benefit in deterring predators or rivals does not outweigh metabolic expense, the trait cannot persist. That it has persisted suggests consistent utility across generations. In the wet season, when vegetation thickens and insects multiply, the lizard's world changes. Abundant cover reduces reliance on display, and prey density increases feeding success. In the dry season, open ground expands and predator visibility improves. Display may become more frequent, but so does risk. Fire, a recurring force in Australian savannas, reshapes habitat structure, temporarily stripping cover and exposing both predator and prey. After a burn, frilled lizards often retreat deeper into surviving trees, adjusting spatial behavior to altered terrain. The savanna quiets again as afternoon heat intensifies. Cicadas drone and shadows shrink beneath trunks. The frilled lizard remains high on its perch, body angled away from direct sun to prevent overheating. It will descend again when conditions moderate, hunting insects drawn to residual warmth in soil. The frill lies folded, inconspicuous, a dormant banner awaiting necessity. It is a testament to evolution's nuanced calculus. Sometimes survival depends not on strength, but on convincing an opponent that strength exists. Bluff is a strategy encoded in skin and cartilage, refined through countless encounters in which hesitation meant escape. But bluff is not invincibility. When predators refuse to acknowledge the illusion, the frill becomes decoration. In that moment, only speed, terrain, and timing remain. The frilled lizard embodies this precarious balance between appearance and outcome, reminding us that in the wild, display is negotiation, not guarantee. The first mistake happens on the ground, but the decision that ends it is made in the sky. High above the Australian interior, where heat shimmers off red soil and spinifex grass rattles in a dry wind, a wedge-tailed eagle circles so high it appears almost motionless, a dark cruciform shape suspended against a pale blue vault. From below, it looks distant, almost decorative. From its vantage point, nothing on the ground is distant. Every movement writes itself clearly across the landscape. The wedge-tailed eagle is built for altitude. With a wingspan that can exceed 2.3 meters, it is Australia's largest bird of prey, and that size is not excess. It is strategy. Long, broad wings with deeply fingered primaries allow it to read columns of rising warm air, thermals that spiral upward from sun-baked plains. By subtly adjusting the angle of each feather, the eagle converts heat into lift, climbing hundreds of meters without a single wing beat. Thermoregulation and flight efficiency intertwine here. The same solar radiation that drives reptiles into shade creates the invisible elevators that carry this predator into its surveillance tower. While mammals below must constantly manage body temperature through panting, burrowing, or seeking shadow, the eagle rides the thermal gradient itself, letting physics extend its patrol range. Vision is the first weapon. The eagle's eyes are proportionally massive, packed with photoreceptors that allow it to resolve detail at extraordinary distances. Studies of raptors suggest visual acuity several times sharper than that of humans. An object the size of a rabbit shifting in grass can register as a flicker of contrast even from a kilometer away. The retina is layered for motion detection, and the forward placement of the eyes provides acute depth perception. What looks like random scurrying to us is a series of vectors and angles to the eagle, direction of travel, speed, likelihood of cover. It does not need chaos. It needs pattern. Below, an eastern grey kangaroo grazes at the margin of open ground and scattered shrubs. Kangaroos evolved for endurance, bounding across wide spaces, their tendons acting as elastic springs that recycle energy with each hop. On flat terrain, few terrestrial predators can match that efficiency. But open ground is a double-edged adaptation. The very landscapes that favor speed also expose movement to aerial observers. A startled kangaroo that bolts across a clearing traces a clean, predictable line, long arcs that advertise trajectory from above. The eagle does not dive immediately. Timing is lethal because it is selective. From altitude, the bird measures not just prey, but terrain. Pressure from above is rarely about a single strike. It is about steering. Raptors often exploit what ecologists call the landscape of fear, manipulating prey behavior so that the environment finishes the job. A shadow passing overhead can trigger panic. Panic favors speed over direction. Direction determines outcome. As the eagle tightens its circle, it edges down the thermal column, lowering incrementally until details sharpen. The outline of shrubs, the texture of soil, the subtle dip of a dry creek bed. The kangaroo senses something, a shift in light, a tightening in the flock of galahs that erupt from nearby trees, and launches into motion. It runs toward what appears to be safety, a patch of uneven ground broken by low branches and rocks. From ground level, that terrain offers concealment. From the sky, it is a trap of obstacles. The wedge-tailed eagle folds its wings partially and tips into a controlled descent. Contrary to popular imagery, large eagles rarely perform extreme vertical stoops like peregrine falcons. Their mass favors a powerful gliding attack that balances speed with maneuverability. As it drops, the eagle adjusts tail feathers like rudders, fine-tuning its approach to intersect the prey's projected path rather than chasing directly. Predation from above is geometry more than fury. The kangaroo, now committed to a direction, encounters the broken ground. Bounding becomes stuttered. Each landing must be recalculated around rocks and scrub. In that split second of reduced efficiency, the cost of panic becomes visible. The eagle extends its talons, curved, needle-sharp claws powered by formidable flexor muscles. Grip strength in large eagles is sufficient to puncture and immobilize medium-sized mammals. Tendons lock reflexively upon contact, minimizing energy expenditure during restraint. The strike aims not for spectacle but for control. Shoulders, spine, the junction where movement can be halted. Even when prey exceeds what an eagle can carry, immobilization is enough. Wedge-tailed eagles are opportunistic and adaptable. They take rabbits, wallabies, reptiles, and carrion, adjusting diet according to availability. In arid regions, where rainfall pulses unpredictably and prey populations boom and crash, flexibility is survival. Their territories can span vast distances, and pairs often maintain long-term bonds, reinforcing aerial patrol routes year after year. This is not random violence. It is an ecological role shaped by scarcity. The pressure from above extends beyond individual hunts. Small mammals alter foraging times and habitat choices in response to raptor presence. Open paddocks become riskier at midday when thermals are strongest and eagles soar highest. Some species shift activity toward dawn or dusk, trading one set of predators for another. Thus, the eagle influences the rhythm of the ecosystem, not merely through consumption, but through the anticipation of consumption. Movement itself becomes strategic currency. There is an irony in how invisibility works here. On the ground, concealment relies on blending with texture, fur against grass, feathers against bark. In the sky, concealment is scale. The eagle is so high that it vanishes into brightness, a dark speck easily dismissed. Yet altitude magnifies power. With gravity as ally, every meter of height converts to kinetic advantage. The landscape below is mapped in advance. The prey does not even know it has been selected. Occasionally, the eagle targets more formidable animals, young kangaroos, large reptiles, even lambs in pastoral regions. This has historically brought it into conflict with humans, leading to persecution based on exaggerated claims of livestock predation. Modern ecological studies, however, reveal a nuanced picture. While capable hunters, wedge-tailed eagles also perform critical scavenging services, removing carcasses that might otherwise harbor disease. Their broad diet stabilizes food webs by damping extreme population fluctuations in smaller prey species. Thermoregulation again shapes the day's hunt. As the sun lowers, thermals weaken, and soaring becomes energetically expensive. The eagle shifts to ridge lifts, using wind deflected upward by hills or perches strategically to scan from elevated vantage points. Even at rest, the head tilts and pivots, binocular focus narrowing on subtle movements. The nervous system of a raptor is tuned to detect the smallest anomaly, a rustle against prevailing wind direction, a flash of fur where shadow should dominate. The mistake that seals fate is rarely dramatic. It is often a matter of running straight when unpredictability would help, of choosing open ground when broken terrain could conceal, or of pausing a fraction too long before bolting. Prey species evolve countermeasures, erratic zigzagging, freezing behaviors, group vigilance, but none are foolproof. Evolution arms both hunter and hunted with incremental advantages, and each encounter tests those margins. From above, the world is stripped to essentials: contrast, motion, exposure. The wedge-tailed eagle does not rush because it does not need to. Altitude grants patience. Patience allows precision. When it finally descends with intent, it is not responding to chaos. It is concluding an equation already solved in the sky. As the light softens and heat dissipates, the eagle climbs once more, circling higher until it becomes indistinguishable from the vastness overhead. On the ground, grazing resumes cautiously. The lesson lingers in muscle memory. Open ground panic writes a predictable story. In this ecosystem, survival depends not only on speed, but on how that speed is directed. The sky predator ends movement mistakes not through relentless pursuit, but by transforming the landscape into a map and every miscalculated line into opportunity.